Hello, am I audible? Okay. Welcome to my talk about functional programming patterns. It's great to be back here after 5 years. Um, I'm Abhinav. I'm a senior software engineer in Google Search, and that's my social media handle. Now, I know that most of the people here probably have used Clojure or some other functional programming language, but how many of you here have worked in Java or C++ or something like that? Okay, that's actually a fair number of people. That's nice to know. So, what is the biggest challenge for programmers these days? I think it's complexity, right? So, thanks to Moore's law and improvement in runtimes and compilers and people's skills in making software, I guess, we generally don't care about the performance of the programs that we write, in the sense that they are worth the money that we put in for writing them. So because of that, we are writing more and more software, and more real world processes and things are being implemented over software, right? This has led to the software being more complex than ever it has ever been, even though software industry is probably like 50 years old only, right? But even then, we have reached such levels of complexity that it's often gets hard to write software, right? Now, complexity is something, people have an innate understanding of people. When I say people, I mean programmers have some sort of innate understanding of what complexity is, right? I'd say that complexity is the degree of entanglement in the software that you write. So I'm sure you have seen complex databases. These are the code bases that nobody wants to touch, right? Nobody wants to go make changes there. Nobody, wants to try out new things. And that's because these code bases are, sort of fragile and also somewhat mysterious, right? So complex code bases are caused by a large number of interactions between a large number of parts, different parts of the code base, right? So as the number of parts and the number of interactions grows, as the number of parts grows, the number of interactions increase exponentially, right? And the code base eventually becomes entangled. And things break in mysterious ways. You make a change here, something breaks over there. You try to fix one bug, and then 3 new bugs come up, right? So complex programs are hard to understand, and hence they're hard to change. Fred Brooks discussed complexity in great detail in his 1986 paper called No Silver Bullet, in which he classified complexity in software in 2 categories: essential complexity and accidental complexity, right? So essential complexity is essential. You're trying to find shortest path between 2 nodes. You have to implement breadth first search or depth first search or some sort of algorithm, right? It's unavoidable. It is what you're trying to accomplish, right? Regardless of how you do it, right? Accidental complexity, on the other hand, is not inherent to the problem, and it's basically, it comes because of the way you're trying to do whatever you're trying to do, right? So say that you choose to use C, right? So you have to do memory management now, right? You choose to use Java now to model everything as objects, even though that may not be what your problem needs to do, right? If you chose to use Node, then you have to deal with like millions of dependencies and supply chain attacks and stuff, right? So accidental complexity turns your software into a Rube Goldberg machine, right? It's like you don't know what's going on. it breaks, again, as I said, it breaks very easily and like mysteriously. And as programmers, we want to do exact opposite of this. We want to write programs which are easy to understand, easy to maintain, easy to change, and easy to evolve over time, right? And I claim that functional programming helps us in reducing the accidental complexity of the software that we write. So, what is functional programming? Now, again, since it's a Clojure conference, I think a lot of people have some understanding of what functional programming is. Now, this definition is, I took it from Wikipedia because it's a controversial topic. Pure functional programming, right? I put pure there in bracket because of a reason I'll mention. So it's a programming paradigm which treats computations as evaluation of mathematical functions, right? And it avoids state changing code and mutable data. Now, that's what pure functional programming is. We, as Clojure developers and a lot of other functional programming languages these days do not do pure functional programming, right? But it is something that we should aspire towards because in my opinion, it leads to, again, less accidental complexity, right? So what are important aspects of functional programming? Again, this is something you may be very familiar with. At least coming from a pure functional programming or maybe like coming from the view of aspiring towards pure functional programming, we want pure functions, which means that a function's output depends only on its input and nothing else, right? So no state, no external, reading from disk or network or whatever else, right? They are easy to reason and reason about. They are easy to debug because, again, no mutable state. They're easier to test because there are no dependencies. You just give some input to expect the output that is expected, and it should work, right? Second aspect is first class and higher order functions. That means that you can store functions in data structures. You can pass functions to other functions, return them from other functions, right, etc. And the functions which take or return functions are called higher order functions. Next one is either no mutable state or constrained mutable state, right? So mutable state essentially causes unseen coupling between different components in your program, right? So instead of talking through calling functions from one component to other component or passing some data, etc., components start talking to each other through mutating each other's state, right? So when I say mutable state, I mean shared mutable state, right? That again causes strange unknown bugs, and it generally makes your program hard to debug and hard to understand, right? So FP tries to have as less mutable state as possible, if no mutable state if possible, and if there is, then it should be easy to constrain it to a small part of your program, right? These days, functional programming languages prefer to be immutable by default. They, like Clojure, they'll have immutable data structures, Clojure, Elixir, all the new functional programming languages that are coming up, right? And you can still have mutability, but you need to do specific things in order to achieve that, right? And the next one I'd say is no or constrained side effects, right? So side effects are any changes that do not depend on your function's input, right? Like writing to a disk, talking to a network, making some state change, etc., right? So again, functional programming will try to constrain the side effects or mark them explicitly so that they are easy to find and easy to debug. And the last one, which is sort of optional but is generally present in all functional programming languages, is lazy evaluation in some form. Some languages have complete completely opted into lazy evaluation. Everything is lazy, like Haskell. And then in Clojure, for example, you have lazy sequences, which are also used widely, right? So some sort of lazy evaluation is useful because it helps, again, to decouple parts of your program via lazy sequences in between, and sort of emulates or simulates a stateful nature, in the sense that like you can imagine that the various like values in a lazy sequence are the state of the program over time. So it sort of like simulates a change in state without actually changing state. So a lot of functional programming languages will have some sort of lazy evaluation, right? So that's what I think are the most important things in a functional programming language, right? Let's look at some example. This is in JavaScript. You have array of some array of objects or maps, right? And you write this sort of a pipeline where you have higher order functions and first class functions to sort of sum up the total members of active programming language communities, right? So just to give you an idea if you are not familiar with functional programming, right? So that brings us to Clojure, right? So Clojure is a functional programming language. Again, I'm sure most of you are already like familiar with it, right? It's a dynamically typed functional programming language from the Lisp family, and it runs on JVM, right? A lot of things have already been said about Clojure, so I'll skip that part. This is the same example, again in the one we saw in JavaScript 2 slides back. This time it's written in Clojure, and it's looks very similar to the JavaScript examples. You have filter, map, reduce, etc., right? Except if you count the number of parents, it's exactly the double of the JavaScript one, right? So in the rest of my talk, I'll give examples in Clojure and Java, right? Some Java examples are for contrast to Clojure examples, like how things are done in Java world or non-functional world. Some of them actually show how functional programming can be done in Java as well, because Java is one of the most used programming languages, and now it has a lot of functional programming features. So we can use that to compare and contrast how things work in Clojure. So this talk is about functional programming patterns. That brings us, the first question is, what is a pattern, right? This is a quote from Christopher Alexander from this book called A Pattern Language. Here the context is architecture, but I think it holds in software world as well. That's why we call, there are software architects. A pattern is essentially a solution to a frequently occurring problem, which you can use again and again with minimal change, right? They're often called design patterns as well, but that term is sort of overloaded, so I'm just going to call them programming patterns, right? In this talk, we are going to go over some programming patterns that I have noticed that work well in functional programming languages. Again, these are my sort of like the things that I have noticed. This is not a complete list. This is not even a top 5 list or something. These are just things I noticed and I found useful, right? So I'm sure there are more patterns, and you yourself may be familiar with something which I don't know about. So please feel free to talk about that after the talk, right? So here are the 5 things we are going to talk about, right? Immutable data and explicit state, data flow programming, explicit over implicit, data-oriented programming, and finally functional core and imperative shell, right? This is ordered, it's ordered in the most used to least used sort of order, as I have noticed in code bases. They are also in the order of easiest to use to from easiest to use to hardest to use, right? In fact, the first one is so easy to use that it's pervasive, like it's everywhere now, the immutable data part, right? You don't even notice it. But only like a couple of decades back, there was it was almost impossible to find programming languages with immutable data structures, right? So yeah, going forward, first one, immutable data and explicit state. The idea is that all your data or objects or structs or whatever you call them, right, once created cannot be changed, right? This used to be a big no-no back then when performance was like a big deal, but now it's like computers and compilers and runtimes are so fast that it's completely okay to create new object for like hundreds of thousands of objects every second, right? So the idea is that all of your domain objects should be immutable, like things like users, accounts, transactions, events, everything, right? Everything should be immutable. The benefit, of course, is their immutability by its nature will not let, if you give an immutable object to another component, another part of the program, it will not suddenly change it so that something in your code breaks, right? It's just not possible. Similarly, thread safety. It used to be a big deal, how to lock objects and how to do mutexes and semaphores and stuff when sharing objects between threads, right? But with immutable objects, you just don't have to think about those things because they never change, right? They're easier to reason about, again, because they never change. And now, these days, or I would say like since last 10 years or so, at least 10 to 15 years, they are very cheap. It's not a bottleneck anymore. You don't need any flywheel pattern or flywheel is the wrong word. It's the one that people used to do, where they created a cache of objects and then borrowed out of that object pooling and stuff. So you don't have to do those things anymore. GC is very fast. Machines are very fast. Compilers are very fast. So you don't have to think about these things at all, right? Let me give some examples. In Java version less than 14, you would use these auto value or Lombok libraries to create immutable data structures. After Java 14, they are built into Java, right? As I said, that more and more languages are moving towards immutable data structures. In Clojure always had immutable data structures, so you just use built-in data structures like vectors and maps and lists. They are immutable, right? Clojure has one benefit over Java, is that the immutable data structures are also persistent in the sense that they share memory, so they are more memory efficient than the Java ones, for example, right? Some example in Java, this is Java less than 14. This is using Lombok, so you have this class and then you put some annotations over it and it generates a class with no setters, only getters. So you can get the name and then you can change the name but get a copy of the object. So the older Abhinav object is a copy with the name, with the age changed, and if you it does not change the age in the original object, right? After Java 14, you would use a record, right? You'll have to write this with age function and return a copy yourself, but it works in the same way, right? In Clojure, you would use a map, right? So something like this, and again, you can use map operations to change the value, but it again returns a copy, so it does not change the original structure, original object, right? The second aspect of this pattern is explicit state. So if most of the things are immutable, most of the things do not change, the things that do change are marked explicitly, right? So of course, you're doing programming, things will change, right? Because programming is a reflection of things you're trying to do in real world, and real world things change, time progresses. So you need mutable state, but you should constrain them. And generally, mutable states are used in things like connection pools, dynamic configs, caches, and stuff like that. If you look a little hard, then you'd realize that most of the domain objects do not need to change, right? So you constrain mutability. By that, you know that if something goes wrong, something is wrong in yours, so there's some bug, something is breaking, then you would have you already know that it's probably because the value in my cache is stale or the thread pool is not configured properly or stuff like that, right? And since you constrain these, you implement proper thread safety. So whatever thread pool you have, whatever thing you're using for caching will have proper mutexes and stuff like that, so that you don't have to worry about those things, right? So this is again a quick example in Clojure. In Clojure we use atoms for this, among other things. So this is the same example, but this time it's shoved inside an atom. So now you can use swap and reset to change the values inside the atom, and it almost behaves like a mutable object, right? You can even call functions on the object, like like this, where you can do multiple of these. This function is called in the swap over here. Okay, so you can call a function and changes the value inside more than one value at one time, right? You can do this in Java as well. So this is an immutable object, and then you put it inside an atomic reference, which is very similar to atom. Quite possibly atoms are implemented using atomic references, I'm not sure. But similar operations here. You have update and get, where you can pass a function. You have set, you have get, and stuff, right? So to summarize this pattern, you have in Clojure use atom, agent, or ref for explicit state. In Java use atomic reference, or you can use actor libraries like Quasar or Akka, right? You can if you're using dependency injection libraries like Juice or Dagger, then you can use what are called scopes to constrain mutability, like in the sense that some mutable thread pool is available only in the database related code and not in your rendering code, for example, right? So you can constrain the scope of mutable components like that. There are also persistent data structures like Clojure for Java. There's Waver and P collections. These are very much similar to the Clojure maps and vectors, but in Java, right? Now moving on to the second one, which is a little more interesting. As we go forward, it will become more and more interesting, as I said, easier to harder to implement, and also more interesting. The next one is data flow programming. Data flow programming is something which models a program as a graph of data flowing between different nodes of computation. Now you may have already been doing this without knowing this name, right? Or you may have explicitly decided to write your code as a data flow program, right? So one example here I have in Java is sort of like a outline of a compiler, right? So you have this first function which returns you some file. The second one takes those files, returns you some token. Third one gives you an AST, and then you see that how each function takes the previous function's output and then returns you a new thing, which is then put in the next function, and finally some assembly files are written down, right? So in Clojure, this will look like something like this, right? Where you can see the threading is more explicit. You don't have temporary variables in between. You just say thread these functions. That's it, right? So this is basically a simple, or rather a simple example of data flow programming, where you have data flowing only in one direction and only in one, in the sense only in one linearly, right? So you one function to another one, to another one, right? This is how you look like if you depict it pictorially, right? The data flows in one direction and it's linear, right? Now there's no need for data flow program to be linear, right? So we'll see more examples later. The idea still remains that each of the data that is flowing between the files, the tokens and AST, everything is immutable, right? And each operation there does only one thing, right? So tokenize just does tokenize, does not do parsing. The next one does parsing, and etc., etc. The operations are put together in some order or composed in some order to get the full functionality, in this case the full functionality of a compiler, right? And this is better because it's very easy to extend. You want to do semantic analysis in between, you put another operation in between, that's it, you're done. You don't have to change all your code base, right? If you want to if you want to pretty print something while compiling it, you just fork the data flow and then you just have another flow over there which prints stuff in between. Works fine. Very easy to extend. Of course, very easy to test also, because each thing does a very simple, possibly not simple, but only one thing, and you can just test that thing. And it's just pure, it's sort of a pure function. Its input depends on its output, so you can test it independently, right? And if this is like, something you write in production, then you can like, monitor each component separately. You can have observability for separate components. You don't have to care about other things, right? You add a new things, you add some monitoring for it, you're done, right? So where is the state in this case? So the state is hidden inside, if there is state, it is hidden inside each function. Each function or each component will keep its own state and it will not share it outside. So it's, if there is mutable state, it's not shared, right? If you use lazy data structures like lazy sequences as the data that flows between different computation points, then this essentially becomes streaming computation, as in the data will stream from the beginning to the end without intermediate data structures and stuff like that. So you get more efficiency, right? So this is another example. This is a middleware over some handler in a web request. A request comes in, the response goes out. If you are doing this, if your request and response objects are immutable, then this is also data flow programming, except now it's happening in two directions. It comes in and goes out, right? This is a more extensive example from a game I wrote when I was learning Clojure. And I'm sorry. As you can see, there are like so many different components, and there are so many flows in between with different colors and stuff. Like it's sort of a Pong sort of game which you play in browser. So you have the keyboard event comes in, which is the buttons you press. The ticker event comes from the browser, and then there's a ball positioner, there's a paddle positioner, there's computations and stuff that happen. There's collision detector, which takes all these sort of data and then outputs the game state and stuff like that. It's all connected, right? And this all is like, I did write all of these as separate things, and then I just glued them using these. In this case, it was Clojure, so I used co-async channels, and I just glued them together, and it just worked, right? In fact, I can just show you the code. This is how the connection looks like, right? In the beginning, you read some bunch of data from a bunch of channels, which is the immutable data, and then you do some computation. At the very end, you just write the output to some other channels, right? The game state and the velocity and stuff like that goes out, right? So clean, right? And you don't have to care, like, each one of these functions, their next position, detect X collision, etc., etc. All of these are independent functions, pure functions, which take some data, does some, output and stuff. I can test them separately. I can change them separately. I can add more stuff in between. It all just works seamlessly, right? So this is a more extensive example of data flow programming. Again, data flow programming is actually quite pervasive in Clojure. I've seen a lot of production software use data flow programming, especially which do any kind of ETL, any kind of background jobs and stuff like that you would lay it out as, or you should lay it out as a data flow program, right? In Java, you would use an actor library, maybe like in Akka, right? Or you can use Dagger producers, which can also be used for sort of like data flow programming. It's more of a graph computation kind of thing. You can create your own using array blocking queue or executor service, stuff like that, right? And I've done that by myself when I was, when these libraries did not exist. In Clojure, just use core async, it'll just all work fine, right? It has a lot of functionalities for all kinds of different kinds of composition of these data flow channels. Like, if you want to join a bunch of channels together and do a fan out, fan in, you can do tapping, you can do like, selectively muting channels depending on events they come. You can create very complex data flow programs, but they'll still be simpler if you did not do it, if you did it without data flow programming, right? So that's for data flow programming. The next one is, the next pattern is called explicit over implicit, right? Can someone give me a time check? Okay. Explicit over implicit, right? So this is 10 minutes? Okay. This is something, this is a bit controversial. A lot of people like magic in their code. Right? They want, things to happen automatically, things to be hidden from view, and like, some library or some framework takes care of most of the stuff, right? But I think or I see, as I see in functional programming languages, that they prefer to be more explicit, right? They would prefer no hidden state, no hidden code generation, no thread locals, no hidden middlewares, no aspect-oriented programming. I've never seen aspect-oriented programming in functional programs, no global state, etc. Right? I'm not sure if all of these terms are known to you, but if you have worked in any large Java or C# kind of code bases, then you would definitely find these kind of things, right? In place of these, functional programming languages, including Clojure, would prefer these, right? So instead of singletons, you would prefer dependency injection, either in terms of some component, like the component library, or in terms of passing the dependencies explicitly as parameters and stuff like that. Instead of aspect-oriented programming to do like, cross-cutting concern, you would use higher order functions, right? So I'll show some examples soon. Macros can also be used for a similar purpose, right? Instead of having like, hidden state, you would use explicit stateful components like atoms and refs and stuff, right? And passing context as functional parameters, right? So some examples follow. This is an example in Java. This is how you write sort of a JDBC transaction. In Java, you put this @transactional annotation over it, and it just does everything magically. You don't know what is going on unless you go read the docs and try to figure things out. It just works, right? In Clojure, you would actually do it like this, right? You would pass the transaction. This is a macro, so it creates a transaction. You pass the DB pool, and then it creates a transaction. You would pass the transaction to the following, the functions inside, and they would all run in the same transaction, right? So it's explicit here. The transaction is explicit here, right? And I think that with a large code base which you have to maintain over a long time, explicit is better, right? This is another example, this time of sort of a web routing kind of case in Java, where you have these annotations all doing some sort of like routing stuff, and you don't actually know what's happening. You just magically run somehow, right? In Clojure, you would do something like this, right, where you pass in a map with some parameters and some context and such to an actual function, and which can do checking for you and stuff like that, and call the handler later on, right? So this is explicit compared to the previous one, right? This is an example of middlewares in Clojure, where you just put the middlewares explicitly, right? Like it's everything. If you go check this code, you know exactly what is happening. There's no hidden stuff, nothing behind the scenes, right? This is the third pattern. Moving on to the next one, right? Data-oriented programming. This, I think, is very powerful, but often not used, or not used often enough, right? But if you look at a lot of interesting code bases will have these kind of this pattern, right? So data obviously is easier to manipulate than functions. You cannot map a function over a body of a function, right? You cannot change a function from a library, right? Given a data, you can do different kinds of things with it. You can print it, you can send it over network, you can interpret it, you can change it to some other data and stuff like that, right? And of course, you can serialize it and stuff, right? So looking at some examples of data as data-oriented programming, this is data as control flow. I'm sure some of you may have seen this thing, where an API is being described in terms of maps and vectors and symbols and function references and stuff, right? So the good thing about this is that if you want to add another route in a different part of code, you can just like take this routes object and then put another thing in between that, and it'll just become active, right? You can manipulate you can pass this object to another function which can manipulate the internals and then add some sort of proxying over it, some sort of security handling and stuff like that. All of that is possible because it's a data structure, not an actual function, right? Another example is data as control flow is logic programming, where you have, like, for example, solving a Sudoku puzzle, right? So if you have a logic program which can solve Sudoku puzzle, the puzzle itself is represented as a data, right? Like array of array and kind of stuff. And then, the logic program will solve this thing, right? So the logic program itself will written in terms of data, in terms of like constraints. It will say that all numbers should be unique in a row and are unique in a column and stuff like that. And then some internal SAT solver or whatever like else will like solve it, right? So that is another example of data as control flow. Data as instructions is also quite pervasive. You may have seen some of rule engines, right? Where this is an example in Java which is very verbose. In Clojure it will be much simpler, right? Where you instead of writing actual functions or actual operations and stuff, you would write rules where say that if this happens, that happens. If the value is more than this and whatever else, etc., etc. And then you give this rule to a rule engine which will take inputs from outside and then execute these rules and do something or something else. Right? This is data as instruction. Another example is interpreters, right? Where you treat data as code, right? So given some data, you can interpret it to do different operations, right? This is a very nice example from Raghavardhani, which turns your data represented here as Clojure maps and such into music, right? So you have these, I don't even know what they're called, but Srihari is right here and he wrote this. So you pass data here and, and it's very easy to manipulate. Again, it's just vectors and maps and stuff, and, it is interpreted to play music, right? There are more examples. Data, for example, data code generation from data, right? This is a popular library in Clojure, HoneySQL, where you represent Clojure queries as, SQL queries as Clojure data structures, right? This is a data structure. Pass it to this QSQL map and it will give you the query, right? The good thing about this is that you can do things with this data structure. For example, you can, in this example, I change the select to add another column in the select by doing this update, and it gets added to the query, right? In this case, I merge a where condition gets added to the query, right? So it just works because data is much easier to manipulate, in this case, SQL program or a string, right? In fact, I've written I've used this in production to write code which generates hundreds of lines of long SQL queries, but the actual functions, each one of them which do this kind of manipulation, are very small, like two, three lines. You just compose them in different ways depending on the query from outside, and then it generates different kinds of queries, querying different kinds of tables, joining them differently and stuff like that. Very powerful thing, right? Another example is data as finite state machine, right? So this is the same thing represented in code here. You see there's almost no code here. It's just data structures, right? This is using the Tilakon library in Clojure, right? So you represent the turnstile as transitions and states like that, and then actions and stuff, and then you finally say that at the very end you say that these are the sequence of action I want to do: coin push, coin push, whatever, and then run these, apply these signals on the turnstile data, state machine, and then finally print out the coin count and the pass count, right? So it is as if it's code, but it's not. It's just data, and it's very easy to save on disk, pass it to network, manipulate, do all kinds of stuff, right? So that's it for this pattern. The last one that we are moving to, as I said, that this is the hardest to apply, but also most powerful, right? You have to opt into this at the very beginning when you start writing your code, when you start designing your project. But if you choose to do it like this, then it gives you a lot of power, right? In fact, it's again used a lot. You may not know the term, but it's there everywhere. So the idea is that you break your code, you break your program into two parts. One is the functional core, right? And one is the imperative shell. So in the functional core, there are only pure functions. There are no side effects, and you put as much business logic as possible in the functional core, right? So no reading from file, no web request, no nothing, no disk, no caching, nothing, right? only pure functions. All business logic goes here. You do math here. You do whatever you want to do, statistics or whatever, machine learning and rule engine and all kinds of previous things. Another thing I forgot to mention is that these patterns are sort of telescopic in the sense that each later pattern contains the previous pattern. So to do functional core and imperative shell, you would sort of do data as instructions inside the functional core. You may do, right? So you make the functional core as big as possible, and then you create an imperative shell which only does side effect. No business logic, no computations, no math, nothing, right? So there you only deal with side effects, right? Like error handling, state, I/O, talking to network, creating web connections, WebSocket, whatever else you want to do. But you should not make any decisions, business decisions there, as few as possible. It should be just to take the data from the outside world, turn it into something your functional core can understand, and pass it on the functional core, and do the opposite on the way back, right? No business logic at that point, right? Because it's very hard to test, because it involves I/O, it involves starting a web server or whatever else. So you make it as thin as possible, as less code as possible. As soon as possible, you take the web request, turn it into a JSON object or whatever Clojure object, pass it to the functional core, and that's it. That's what the imperative shell does, right? This is also quite popular in front ends these days, right? This is the Mobius architecture for creating Android apps using the Mobius framework, right? So you see that here you have a pure layer and an impure layer. Impure layer is like effect handler, event source, user interface and stuff. Pure layer is where all the business logic lives, and these arrows are basically the flow of data between these two sides, right? Another one you may be familiar with, is the Redux architecture which is used with React, right? So you have these views and actions which are sort of imperative part, and then you have these reducers, dispatchers, and state and stuff which lives inside your functional core, and then where you run the functions, do business logic and stuff like that, right? So these are the two examples of functional code imperative shell, right? So that is all I have for my talk. These are some references here. This slide is available at the last link right there, and that's my website and that's my social media handle. That's it. Thank you.